Hi, I'm Mike Stevenson from Production Support 56. Today I'm going to talk about the basic elements of manufacturing simulation by demonstrating a model we created to determine if a business should invest in a new piece of equipment. Manufacturing simulation is a useful tool for supporting good decision making. In this unit we're going to talk about the basic building blocks of manufacturing simulation, the important states and the properties of these, how the simulation collects data, and how we can use the model to make predictions and help support good decision making. To demonstrate these ideas, we'll take a look at a model we created to determine if a business should invest in a new piece of equipment. We use manufacturing simulation software for the modelling, as we needed to use complex logic to describe the production line, and we needed time-based results. Before constructing a model, you should always carefully define what you're trying to achieve. Basically, what question do you want answering? It's then easy to collect data and build the model using the question as the focus. Without this focus, you will waste lots of time and effort collecting unnecessary data and building unnecessary model functions. If you have further questions, it's easier to develop an existing model. For this model, we wanted to determine if a business should invest in a new piece of equipment. And to do this, we needed the operational costs of the current and proposed lines. With the operational costs and the capital costs of the new equipment, we can then calculate the payback period, which will then be used to support the investment decision. The models were constructed to calculate the operational costs. For the current state model, we used real performance data from the production line. For the future state model, we combined the performance data with specifications and trial data of the new equipment. Once we've verified the current state model, we are then confident that it can provide us with accurate predictive simulations. So, let's take a first look at the model. The process consists of two main stages, cutting and finishing. The current state runs across the top of the simulation. Here we can see material flow through the cutting and then finishing stages. The business is looking at replacing the cutting stage with new equipment. Now if we stop the model and change the route, we are now sending the material through the new equipment and finishing stages, and we can see the material flow across the bottom of the model. We've created both the current and future state models in the same simulation environment to ensure we have a fair comparison. For this model we're using Simulate software. All manufacturing simulation software uses similar building blocks or entities, but may be called different things. Work items are the focus of the work. This is the raw material that is transformed into a valuable product. The work item could be a part, like a washing machine, materials like sugar, or information like a credit card application form. In a simulation, a work item could represent a single part or ton of materials. You use whatever unit is suitable for your model. The start point brings work items into the simulation environment, and then the endpoint takes them out. The simulation environment should only focus on the areas of interest. Activities are where the work happens and represents a transformation of the work item. These are discrete processes that are carried out at machines, workstations or office desks. Queues are where the work items wait. Typically this is for a work activity to become available, but could also represent a time-dependent process like drying or cooling off period in a contract. Labour represents the human resources required to run a process. These are called off to carry out activities or transport work items. If labour is unavailable, it will cause a delay in the activity. Now let's take another look at the model. The work items are the red dots. In this case, they represent 10 kilograms of material that goes through the cutting and finishing stages. The starting point shows how many work items have entered the simulation, and the end point shows how many have left. The blue bordered boxes represent activities, and the white boxes represent queues. Some of the queues contain work items waiting for activities to become available, or to reach a minimum batch size to be transported. We have two types of labour in this model: supervisors and operators. The activities call off specified labour when it's needed. The numbers here represent unused or idle labour, and as you can see, the numbers go up and down as the labour requirement changes with time. The simulation clock tracks the current time in the simulation. This is a discrete event simulation, in which the software works its way through a series of discrete events. Each event represents a change of state of an entity and has a defined time. The clock appears to jump erratically as the software jumps in time to the next event. In this model, we're only concerned with two states. Idle, this is where an activity is available to work but is waiting for a work item. This could be a worker at a customer service desk waiting for a customer. The other state is busy. This is where an activity is currently working on a work item. This could be a pillar drill drilling a hole in a part. There are other states which are not important to this model, such as blocked, stopped, changeover, and waiting for labour. So let's go back to the model and we can take a closer look. The blue cog with the blue border represents an idle activity. A blue border with a person icon represents a busy activity with labour. And a blue cog with a green border represents a busy activity which doesn't need labour, i.e. it's automatic. To create an accurate simulation, you need to use your process data to define the properties of each entity. The key properties are cycle time. This is the time taken to complete an activity. Resources. This is the number and type of labour needed to carry out an activity. For example, a crane lift may need a crane operator and a banksman. Routing in. This is the location where the activity takes a work item from. It could be a pile of inventory next to a machine or a queue of customers waiting to be served. Routing out. This is where an activity puts a completed work item. Batch size. This is the number of items in a group that are either transported or processed together. For example, eggs may be moved in boxes of a dozen. Capacity. Here we're defining the maximum number of work items that could be stored within an entity. For example, a warehouse may have space for 100 pallets, or an oven the space for 20 loaves of bread. Let's check this out in the model. So let's take a look at the properties of the pack and check activity. We can see it takes on average 8 minutes to complete the activity, and it needs one supervisor and one operator, and it collects 10 work items from the QC holding pen. 5% of the work items are rejected, and the 95% that pass get moved to the storage queue. And if we look at the property of the fill hopper, we can see this has a maximum capacity of 10 work items. As the simulation runs, it continuously collects data on the states of each entity. We can use this data to compile simple statistics such as equipment utilization. And if we rerun the model with different starting parameters, we can then compare the equipment utilizations under different scenarios and identify the optimum conditions. In this model, we combine the data generated by the simulation with external datasets to produce operational costs. So for example, we know the electricity usage of a piece of equipment when it's in an idle state and when it's busy. We also know the price we pay for electricity. The simulation counts the idle and busy time, and from this information we can calculate the total electricity cost of operating that piece of equipment under multiple scenarios. So let's take a final look at the model to see how we do this. So we've set up a couple of dynamic graphs to update throughout the simulation run. These are useful for quickly assessing your process and identifying bottlenecks and constraints. For this model, we can see there are periods when we use all 13 operators for route 1. This may be something we need to further investigate. In this model, we've set up some logic to retrieve relevant data at the end of the simulation run. This is dropped into a spreadsheet. The logic also does some calculations with the data and then creates a P&L for the operational costs. We have three spreadsheets in this model, one for process parameters, one for raw calculations, and the one we're interested in contains the operational P&L. The model has generated resource usage for each stage and converts this to a cost. This is done for the current and future state, and it's done per day and per tonne of product. The model calculates a potential sales revenue and then a gross margin, which is then used to calculate a payback period and a return on investment. So, has the model answered the question, should we buy this new piece of equipment? It's provided us with the operational cost of the current and proposed lines and calculated the payback period, and so overall it makes a positive financial argument for the investment. To make the final decision, it should be considered with other factors, such as technical capability, practicalities, market conditions, and judge this against alternative investments. If these all stack up, then yes, we should buy the new equipment. So we've shown that manufacturing simulation is a useful tool for supporting good decision making. We have covered the basic building blocks of manufacturing simulation, the important states and properties of these, how the simulation collects data, and how we can use the model to make predictions and help support good decision making. If you have any questions, you can get in touch with me with the following contact details. I'm Mike Stevenson from Production Support 56.